Morning, Darcy. Morning, Darcy.
Good morning. How are you?
Very good, very good. We wait for a couple of minutes and then we'll start. Thank you.
Yeah, no, all good.
Okay, good morning, everyone. Shine is here, week 11. Typically on Mondays, we will be running a lecture, and upcoming 4 hours, there will be 2 demonstration or tutorial sessions. So last week, we decided to bring the last lab forward to complete that in week 10. As a result, today, that would be a tutorial for the previous subject, which is internal stress due to the bending stresses. And tomorrow, I will be delivering the lecture for this week. And that would be the last lecture. So tomorrow, we go through the last lecture. And whatever time we got left, that would be spent for exam preparation. We have plenty of examples to be solved, demonstrated, and running the tutorial to get you prepared for the exam. Okay, so just let's make a quick summary. So far, we are studying the beam structures, and the beam structures are generally going through the deformation by showing the change of curvature. So they change the curvature either in a positive way, they change the curvature in a negative way. In some cases, if the loading is complex, you might have a different types of change of radius. So the key question is, well, in some design, we want to know how much deflections is taking place. So calculation of the deflection is beyond the scope of this subject. In many many topics, people wants to know how much deformation is there. And even fracture is a failure mode. Fracture is a failure mode. That means a crack starts and grows. But in some cases, deflection, too much deflection could be a failure mode. Imagine this is a building and people on the roof, when they are walking, they feel the movement under their feet, and that is not acceptable above some level. So depending what the acceptance criteria is, the objectives are different. So in this subject, we are not looking into the deflections. So the deflections of different points are with respect to the datum. So the middle point has here largest deformation. Here maybe this deformation is larger than that one. But in this subject, we are not looking into the deformation calculation, because a key for deformation calculation is a strain. That is the percentage of the dimension changes, and this is not covered in this unit. Okay, what is covered is at some limited scope, we want to find out the maximum internal load. Maximum internal load when there is a bending, when there is a beam, and when there is a bending. There are three types of internal load. The first one is the internal load, which is developing axially. So that changes with X. The internal load which develops due to the shear, and the internal load which develops due to the bending. All right. So all these, for a better comparison and for a evaluation purposes, I mean, we want to bring the material into this. So we need to define a new parameter which is called the stress. Okay, so we know that normal internal force that would cause stress, normal stress in average sense. We know that the bending moment would develop a normal stress as a function of X and Y. And we discussed that this is due to the flexural, can be calculated by flexural formula, bending moment multiplied by the distance of the point from the neutral plane divided by the second moment of inertia. So far, we can calculate these two. Even in the case of the shear, I mean, if that's not a beam, if that is something like a this is a kind of single shear pin. So we know how to calculate the internal force here and also the shearing stress in that pin in average sense. But tomorrow, I'm going to tell you how during the bending a shearing stress would develop, which is a function of X and Y. So that is for tomorrow lecture. But for today, we want to zoom on internal stress, normal stress due to the bending. And then we want to do some calculation. The key is, if I give you a bending scenario, so this is a bending scenario, for example, some distributed load here, some point load here, some reactions, right? And for this general system, A, B, C, D, E, F, you want to know that what is the largest stress over this entire beam. So the domain is going to be two-dimensional in X and Y. So the question in nutshell is, I want to specify X star and Y star. This is the location at which the stress due to the bending is going to be maximum. So we have to scan over the longitudinal direction of X. We have to scan along the transverse direction Y, and then just spot which point, which coordinate corresponds to the point with the maximum normal stress. So that is only half of the problem. Tomorrow, we can find out something like X double star and Y double star, at which the shearing stress is maximum due to the shear stress. This is due to the bending moment. So this is for tomorrow. This is for today. Today, we go through a number of examples. I give you a beam. For that beam, we start plotting the bending moment diagram. And from the bending moment diagram, we just utilize the flextural formula to find out how the normal stress due to the bending changes through the X and Y, and hopefully to find which point develops the largest bending stress. Okay, let's get started. Here I have a problem for you. So in this problem, we would start with solving the internal forces. So before starting internal forces, I have to find out the reaction force. And from the reaction force, I should go through the bending moment diagram. And from bending moment diagram, I find the maximum bending. And from maximum bending, we can go to flexural formula and finding the maximum stress at a certain critical point. So here I summarize the steps for you. Just the first step is reactions. The second step is shear force diagram and bending moment diagram. And then I find the bending diagram X at X star. So from here, I use the flexural formula and find out what coordinate my bending internal bending stress is maximum. Okay, so let's get this one started. All right, I suggest everyone grab a piece of paper and try to calculate the reactions. Let's have 5 minutes for calculating the reactions. 5 minutes start now. Okay, thank you, Darcy. Let's see if your calculations are right. So Darcy found them AY equal to, let me bring this to the solution page. So according to Darcy, that is AY is equal to 4.8 and BY is equal to 4.2. So let's solve this together. I see that now we have also new students in the class. So like I said, the first step is to find out the shear force diagram and bending moment diagram. And also before we can plot them, one needs to find the reactions. So a quick change, I mean, if I want to check the answer by Darcy quickly, a short and fast check that is, let me just adjust this one first. All right, so the total load here is 3 kilonewton. So the units for these are also kilonewton. So a short check, the distributed load is 2 kilonewton per meter multiplied by 3, which is 6 kilonewton. So 6 plus 3 is 9. So the sum of these two should be 9. If I add them together, that is equal to 9. So therefore, the answers provided by Darcy are correct. So let's include these solutions here. AY, which is toward the larger load, that's 4.8. And this is BY equal to 4.2 kilometers. Okay, so that is correct. In case if you want to do the same as Darcy did, you need to just lump the 2 kilonewton force right in the centroid of that distribution, which is 1.5 meter from the left. And then we apply the condition on the free body diagram with two reactions vertically. We apply the condition of net rotation with respect to the A equal to 0, that give you BY. And then again, the second relationship would be net rotation with respect to the B equal to 0, which give you A equal to 4.8 kilonewton. Now, to start solving this problem, I do need to find out the number of the zones. How many zones are here? Zones of loading. There is one zone between here and there. Let me call this point C. I call this one point D. So there is one zone between A to C, second zone between C and D, and third zone between D and B. So there are three zones. Let's start with zone number 1. And here I take my coordinate system located at A. So that makes X changing between 0 to 3. And for that, W of X, okay, so here, 40. What expression should I write for W of X in the first zone? Can you tell? Or Darcy, what equation for W of X? So this is a constant value, but that's a negative one. All right, so that is -2. That is -2. It's a constant, -2 kilonewton per meter. And then the next step is I want to plot the shear force diagram. I know that if I make a section like X, so that is V of X, V exactly at this X, minus VA, that is equal to integral of W of X dx between A to X. All right, so where did I get this one? This is the method of equation. You remember, for making the shear force diagram, the easiest way in these cases are method of equation. So that V of A, I know that V of A is V of A, that is V at x equal to 0. According to Darcy, that is 4.8. Okay, so that makes this one V of x minus 4.8 is equal to integral of minus 2 dx between 0 to x. So that is equal to minus 2x between 0 and x. All right, so here I find v of x is equal to 2x minus 2x plus 4.8. That is the expression for v of x. And I can check this by plugging x equal to 0. That gives me 4.8, which is correct. And also, I want to know what is v of c. If I plug x equal to 3, yes, this is, yeah, let me explain that again. I start from scratch. Okay, is that making sense, Darcy? W of x equal to minus 2. Is that, this is not your question, right? So are you happy with that one? All right, so W of x is a distributed load, and distributed load is a different concept with the point load. That is something like an intensity of the load. And the reason I put this minus 2 because this is pointing down and this is constant. I mean, if that was a linear distribution, we had a line. If that was a quadratic, you have the second order equation. So in this case, because it's a constant negative number, W of x, this is the intensity, that is W minus 2. So that we discussed that in week 9, 10. Okay. All right. Now, the next thing, what is method of equation? I'm trying to summarize that for you, Darcy. We know method of equation is W of x is related to the shear force in a differential way. So if I take derivative of the shear force with respect to the x, that is going to be W of x. All right. So let me expand this relationship for you, Darcy. If I manipulate this equation, that is dv is equal to w dx, right? And then if I take integral from both sides of equation, that is integral of the dv is equal to integral of w dx. And the bound of integral, I take that between the starting point A to an arbitrary point, which is point X. So whatever this point is, I call this point X. So this is X equal to 0. So then, therefore, this integral dv and integral of dv back into the calculus, integral of the dv is vx minus va. So left-hand side is v of x minus v of a, and the right-hand side is integral of minus 2. Integral of minus 2 is minus 2x. And the bound of integral are between x and 0. So here I would have v of x, and v of a, that is the shear force at the beginning, that is minus 4.8. And the right-hand side, the integral of minus 2x evaluated as x is equal to minus 2x. And minus 2x at 0, that is 0. All right. So this one, if I simplify, becomes shear force as a function of x. That is equal to minus 2x plus 4.8. All right, thank you, RC. Anyway, if things are not clear, please stop me to explain again. All right, now that I have V of X, the next step would be to use another method of equation to find the bending moment. And then I know for the fact that bending moment is the derivative of the V of X. So if I have V of X by one time in differentiation, that gives me M of X. So let me manipulate this equation again. That is M of X dx is equal to dV. So from both sides of here, I take an integral between between a to x. Yeah, this is not right. I think I got the equation wrong. Let me write the equation again. So the right equation is V of X, that is equal to dm of X with respect to X. So if you have the bending moment as a function of X, all you have to do is by taking its X derivative, that is going to be equal to the shear force. So I would manipulate this equation, that is dm is equal to v dx. And then from both sides of this one, if we integrate, that becomes, so let's substitute this value here, and then, all right, so let's look at the solution. This problem at point A, that is a pin, and pin doesn't resist against the rotation. So what that means is the bending moment at point A, the bending moment at point A, that is m at x equal to 0, this is equal to 0. I know that from the solution of the beam. When we found the reaction, I know that. So this one, if you expand, this becomes m of x minus m of a is equal to integral of this guy over there. Okay, that is integral of minus 2x plus 4.8 dx. And the bound of integral are between x equal to 0 to x. So left-hand side, that is m of x, and m of a is 0, right? So this is 0 minus 0. And what is that integral? Integral of minus 2x, that is minus x2, right? And the integral of 4.8, that is plus 4.8x. So just take a derivative. That derivative is minus 2x. This derivative is 4.8. So that the bound of integral are between 0 to x, which is equal to minus x2 plus 4.8x. So just let's summarize this equation. M of x in the first zone becomes minus x2 plus 4.8x. So can we check this? So plugging x equal to 0, that gives m equal to 0. That is correct. And at the end, x equal to 3, m is equal to minus 9 plus that. Let me calculate this one. 9 minus plus 4.8 multiplied by 3, 5.5. And the unit is kilonewton meter. All right, now we are ready to plot this one. The first plot which we make, that is for the first zone. We plot so to plot v of x, all right, x equal to 0, v of x is equal to 4.8. So this is my shear force diagram, and this is my x-axis. All right, x equal to 3, the shear force is what? At x equal to 3, I need to find out the shear force. That is by plugging x equal to 3. That becomes mv of 3. That is minus 6 plus 4.8. Okay. Minus 1.2. Minus 1.2. So in the first zone, I have the shear force going between plus 4.8 to minus 4.2. And then in the second zone and in the third zone, okay? But just before that, let's finish with the first zone. The first zone, now we can plot also the bending moment. The bending moment can be plotted for the first zone. So I'm cleaning some of these calculations to make room. So the second plot is my bending moment. So this is bending moment diagram. And it starts from 0. And at this end, also, if I plug x equal to 3, m of 3, that is 5.4. Okay, now I notice that shear force going from positive to negative, there is a 0 value here. So let me find the location of this point. The location of this point, because there is a differential relationship between the shear force and the bending moment. Wherever the shear is 0, the bending moment is maximum. That is back to the calculus. Remember, in the calculus, whenever the shear force is 0, the bending moment is maximum. So how can I find that location? Simply, I set this one equal to 0 and find the location of x star. So that is minus 2x star plus 4.8 equal to 0. That gives me x is equal to 2.4 meter. So this is 2.4 meter. All right, so that means I need to calculate m at this coordinate, and that m value would be the maximum bending moment. So this is a quadratic equation for m. We found the quadratic equation for m. So let me just rewrite that equation for m. So by integrating this one, m of x, that is equal to minus x squared plus 4.8. So now m at this x star, which is 2.4, is equal to 2.4 squared negative plus 4.8 multiplied by 2.4. So this is 5.76. And the unit is kilonewton meter. So now I know that the bending moment here is a quadratic. The quadratic with a negative number, negative coefficient, that is an upside down curve. This is an upside down cup. So this would be a quadratic curve like this one, and that is the maximum. The maximum is 5.76. Okay, any questions so far? Any question? You want me to explain any part of this one? Okay, if there is no question, we can move to the second part. Okay. Thank you, Darcy. Let's go to the, thank you, Porty. Let's go to the zone number 2. Zone number 2 is between C and D. And I need to erase all these to start the second one. All right, now we go to the zone number 2. And zone number 2, I would like to bring the coordinate system starting at C. That would simplify the equation. So that is zone number 2. And here, x is changing between 0 to 1. Okay, at zone number 2, what is W of x at zone number 2 between C and D? Porty, do you know what is W of x between C and D? Or Darcy, what is W of x here? Yes, well done. W of x is equal to 0. So then I should use the differential equation. W of x, that is dv over dx. And that means v of c minus v of x, v of x minus v of c, that is integral of 0, which is 0. So that means v of x equal to v of c. So what is v of c? V of c, at the start of the curve, I know that v of c, this is a continuous shear. Look, here, shear is continuous because there is no point load. The only thing which makes the shear force discontinuous is a point load. The distributed load, this is kind of distributed load of W0. So distributed load is always continuous. If you have a point load, that makes your shear force diagram discontinuous. So here, V of C is equal to the last value from the previous, which is minus 1.2. So that is minus 1.2. So it means if I want to continue that curve for the second zone, that doesn't change. It goes from minus to here. All right? And hello. Yes? Not interested. Bye. Okay, so the next step is using the expression for V of x. Now, if I want to summarize that equation, I have for the first zone, V of x is constant, that is equal to minus 1.2 kilonewton. That's the expression for V of x. Now, the next method of equation is V of x is equal to d derivative of m with respect to the x. So if I manipulate that expression, this is dm is equal to integral of the v dx. So dm over that period, that is m of x minus m at 0. So m at 0, what is m at 0? M at 0 is 5.4, and there is no point bending moment there. So this has to be continuous. The left value, right hand value are equal because there is no point bending moment here. So that should remain constant. That is equal to m of x minus 5.4. That is equal to integral of v of x. So let's find out the integral of v of x. That is integral of 1.2 dx between 0 to x. So that is m of x minus 5.4. That is equal to minus 1.2x minus 0. And that you can simplify. Simply m of x is minus 1.2x plus 5.4. And now you can check this one by plugging x equal to 0. M of 0, that is 5.4, which is correct. And also you want to find m at the end of the second zone, that is m of 1. M of 1, that is 5.4 minus 1.2. which is 4.2. So here, that is a equation of a line. This is the equation of the line, and the line has a negative slope. So let's plot the equation of a line with a negative slope. So this is for the second zone. You linearly go from here to here, and from 5.2, you go to 4.2. All right, so now we managed to plot the shear force diagram, the bending moment diagram for the second zone. And the last zone is, let's solve this for the last zone. The last zone, this is zone number 3. Okay, for zone number 3, before I proceed, everyone happy with the zone 2? You want me to repeat anything? All right, thank you, Porty. Let's go to the zone 3. Thank you, Darcy. In the third zone, again, I bring the coordinate system at here. So in that, my x would change between 0 to 1. So the shear force left hand, I call this the shear force D minus. This is the left hand side of point D. The left hand side that is equal to minus 1.2 kilonewton. But when I go to the D at the positive side, there is a discontinuity. 3 kilonewton is subtracted from that. So that would be minus 1.2 minus 3. That becomes minus 4.2 kilonewton. So how are you following? Is that understandable, or do you want me to explain? Can you see why there was a jump in this one? So which value should be used for plotting? Should I use the positive value or negative value? Porty, should I use the positive one or negative one? If I want to plot the shear force, do I take the left hand side or right hand side? Darcy, which value should I use? So now we are in, yes, we have to use right hand side. Well done. That is minus 4.2. And then what is W of x? W of x is again 0. There is 0 distributed force between D and B. So then I have d of v is equal to integral of w dx, which is 0. That means v of x minus vd plus. So therefore, my expression for v of x is minus minus plus, bring that to the right hand side, that becomes minus 4.2 kilonewton. That is my expression, constant. So in the third zone, I would have 4.2 starting here, constant up to here. This is minus 4.2. And then suddenly here, the reaction is 4.2. The 4.2 reaction, bring that back to the 0. So 4.8 at the beginning, 4.2 at the end. So now we completed the shear force diagram. So let's finalize this one by going to M of X. So in the third zone, 1, 2, this is fourth zone, is it? No, that's the third zone. 1, 2, 3. In the third zone, I can write that there is no point bending moment here, so I expect my bending moment to be continuous. From here, this is continuous. So I would have V of X is equal to dm over dx, and therefore this is m of x minus m of d is equal to integral of minus 4.2. So that I can find that m of d is equal to 4.2. So I just plug here, that is m of x is equal to integral of that one is minus 4.2x plus 4.2. So that means m of 0, that is equal to 4.2, and m of 1, which is the endpoint, that is equal to 0. So this is the equation of a line with a negative slope. It means my bending moment goes from 4.2 to 0. Okay, so now, all right, everyone happy with the bending moment diagram we got here? If you want me to explain, just ask. All right, now let's ask ourselves, why did we go through all these calculations? Why did I need to have a plot of shear force, or why did I need to have a plot of bending moment diagram? Do you know why? Anyone knows why? All right, the reason is a plot would help you to find the maximum value. That's why. So we were trying to answer the question. Just by looking at a graph, you can tell where the maximum is. The maximum is the critical point. So remember, when I started the lecture, I said, look, you are investigating a problem, and in this investigation, the final objective is to find x star and y star. X star is where the bending moment is maximum. So we are looking for a maximum stress. So maximum stress is where this beam might grow crack due to the bending. So to find this one, you need two coordinates, x star, y star. X star is where the bending moment is maximum, because according to the flexural formula, that is m max y divided by I. So where is m maximum? All right, Darcy Porty, can you tell me where is the coordinate of the maximum bending moment? Just look at the graph. Yes, exactly. That is my x star. So this is my x star. So if I want to find maximum, what else do I need? From this flexural, I only found m. What is the next thing? I need to find y at which the stress is maximum. Also, I need to find out the second moment of inertia for that section. Let's go back to this problem. This beam has a cross section like so. So the second part of this problem is we have to find out the cross section. We have to find the second moment of inertia for this one. All right. Who can tell me what is the first step if I want to find the second moment of inertia for this section. How do I find the second moment of inertia? All right, the first thing is I have to break that into two pieces, number 1 and number 2. This is a composite shape, number 1, number 2, right? And this is my datum, this is my reference. And first thing first, I need to find the center of area for that composite shape. Center of area for this one, that is y bar. This is equal to, for the first shape, what is the y bar? That is half of this height, that is 10, multiplied by the area. The area is 20 multiplied by 60. And for the second shape, the center is 20 plus 30, which is 50. Sorry. Yeah, this is 20 plus 30. 50 multiplied by divided by 2 times 20, 60. So 10 plus 50 divided by 2. That is 30. Is that what you got? Anyone got a different number? Yeah, 30 is correct. You want me to explain again? Did you follow? Okay, good. Now we have y bar. The next thing is I need to find the I value for that. And for this, I'm making a table. In this table, I write the segment number. There are two segments here. Segment 1, segment 2. And so here I have area of the segment. So the area for this one is 20 times 60, that is 1,200. This is 1,200. The next one is moment of inertia of each from the table. That is from the table. That is 1 over 12 for the first one. BH3, that is 60 multiplied by 20 cubed. That is 40,000. And that is in millimeter. Everything is in millimeter to the power of 4. For the second shape, from the table, what I get is 1 over 12 BH3. B is 20. And H is, again, sorry, that was for the second shape. That was for the second shape. For the first shape, that is different. For the first shape, B is 60. Okay, 20 times 60 cubed. Yeah, that's right. That is 60 cubed multiplied by 20 and divided by 12. That is 360,000. All right. The next thing is I need to calculate the penalty. The penalty is the center of this shape measured from the centroid of the total shape. This is, I call this D1. So D1 is the, or D1 squared. That is the penalty we pay for using the table value. This is from the parallel theorem. So D1 is 30 take away from 10, that is 20. 20, so D1 is 20 millimeter. That squared, this is 400 millimeter squared. And for the second shape, the center of this one is here, which is 60 plus 20, 50. 50 take away from 30, that is 20 again. So D2 is again 20, that is 400. And now the penalty term, that is DI squared multiplied by AI. So here you just add them up. So total I, that is this 40,000, that's from the table, plus the penalty. The penalty is this one. And that is just for the first shape. For the second shape, that is 360,000 plus the penalty. The penalty is the same. And what you get, that will be in millimeter to the power of 4. $1.36 multiplied by 10 to the power of 6 millimeter to the power of 4. All right. Now, with that section, look, this is my neutral plane. With this neutral plane, I know that the definition of the neutral plane, let's have a closer look at the flextural formula. The flextural formula, that is M max. So what is Y max? Y is for a typical point, that is the measure from neutral plane. So this is Y. Can you tell me which point over this cross section has the largest distance from that? Is this that the points on the top or the point at the bottom? Which ones have the largest distance from the neutral plane? Okay, top. Let's calculate the top. The top, the total is 80. 80 take away from 30, that is, so way of the top, Y for the top, that is 80 total, take away y, which is 50. And y from the bottom, that is simply minus 30. So yes, Darcy is correct. The largest maximum is that at the top, which is equal to 50. So the farther from the neutral plane, the larger the normal stress. And then in the denominator, you put this number here, 1.36, 10 to the power of 6. And here, the result would be in megapascal. Well, if M is in Newton millimeter, then the result would be in megapascal. So simply, now we managed to, so in another word, y top is equal to y star. Remember, we're looking for sigma max is sigma at x star and y star. X star was here. X star was here. That is where the bending moment is maximum. And y star is all points here, where the distance from the neutral plane is largest. So y star is equal to, this is sigma of 2.4 and y equal to 50. So that, what was the maximum bending moment? The maximum was 5.76. And let's convert that to Newton millimeter. That is 10 to the power of 6. And the y is 50. And that one in millimeter. So that is 211.76. And the answer is in megapascal. All right, so that was a breathtaking journey. We came all the way to find the maximum stress due to the, yeah, that's the same number. So we came all the way to find out that, look, the points which are here and the point which are in this portion of the beam. So this is X star. And this one is the Y star. Now we managed to find the maximum internal stress due to the bending to be M of X star. That is the maximum M. And multiply by Y star, that is 50, divided by I. And that was 211.76 megapascal. So what it means is the most critical point of this beam due to this bending load would be located right at this section. And this section, if I do a cross section, that is over here. Questions? Any questions? All right. Thank you, Darcy. Thank you, Porty. All right. This is a very laborious, time-consuming type of problems, but For the exam, if you understand what we did today, that is all good for the exam. I mean, exam would have two parts. One of them is the stress due to the bending, and the second one is the stress due to the shear force. Due to the shear force, we go through that tomorrow. Tomorrow, we find out how the shearing stress due to the shear force will change, and then we find the position for the maximum internal shearing stress. That's for tomorrow. But for today, what we did is just enough. That was a moderate to difficult problem. So hopefully in exam you get something easier than this one. If you understood that, you'll be safe. All right, thank you. Let's go. We might have time for another example. In the next example, let's see what is waiting. So that is the distribution. We know that according to flexural formula, this flexural formula, it is telling me that stress is related to y in a linear way. So the larger the y, the larger the max. So the largest is here, 0 is here, and it changes the direction over there. So therefore, linearly, it goes from positive to 0 to negative, or positive, 0, negative. So they change linearly. Here, neutral plane, 0 normal stress, maximum here, second maximum here. First maximum, second maximum. So at the bottom of the beam, that is how much stress you get. At the top of the beam, that is how much stress you get. So as we expected, that the top maximum is first maximum. This is the second maximum, which occurs at the bottom. All right, now we have a, red is first maximum, yellow is the second maximum. All right, for the very same problem, I mean, this is very similar to the previous one. Let me summarize the steps for you. What steps do we take here? The first step is step number 1, finding the reactions. So with the reactions, how many steps? First, you concentrate that force. This is 1.2 multiplied by 5, that is 6. 6 would be right in the middle, okay? And then that would give you A, Y, and BY. So that is the first one. You find the reaction. Once you find the reactions, so the second is how many zones? There is one zone here, second zone here, third zone here. So 3 zones. For each zone, you have to find W of X. Finding W of X, you find V of X. And finding V of X, you find M of X. So once you finish that, you could tell maximum bending moment is occurring at X star. So here you find X star. And then the fourth step, that is you go and find the Y bar for this cross section. So Y bar for this section, you break that one into shape number 1, shape number 2. And using this table, you find Y bar. And from Y bar, you find I for the total composite shape. And then in the fifth step, you plug flexural formula, sigma maximum. So the maximum bending you found from here goes there. And now if I give you the Y bar, can you tell me what the Y star is? So imagine that here, just let me cheat. to get the y bar from here. Y bar is 29.48. So let's assume this is 30. Okay. So if my y bar is equal to 30, okay, can you tell me what is YSR? The point at which the maximum distance from neutral plane is. So my neutral plane is 30 millimeter from the bottom. So which point is more critical? The points which are at the top or the point which are at the bottom? Which one are more critical? Which one is farther from the midplane? The point at the top or the point at the bottom? Yes, well done. The points at the top, these are farther from here. And that is why SR is equal to 90 plus 15, which is 105, minus 30. So YSR becomes 75 millimeter. So in the flexural formula, you put M here, M of X star, and then you put Y star, which is 75. And then you put the I value here. Okay, maybe we do the I calculation for that because all the bending moment diagram has been done for you. This is very similar to the previous one. So what we do is we calculate that part. So let's go through the calculation of this one. All right, I'm breaking this shape into two pieces. This is a composite shape. And this is number one, this is number two. And then my Y bar, this is my datum, this is my reference. So Y bar is Y bar of the first shape multiplied by the area of the first one plus Y bar of the second shape, area of the second shape. And in the denominator, you have A1 plus A2. So that is for the first shape, with respect to that reference, that is 7.5. And the area is 15 times 100. For the second shape, half of 90, this is 45. 45 plus 15, that is 70. So let's do that again. 45 plus, that is 60. 15 plus 45, 60. And the area is 90 times 12. Okay, denominator, you have 1,500 plus Yeah, that's 29, 70, 48. All right, now let me form a table. In this table, I put the shape numbers here. So first thing first, that is the area of the first shape in the millimeter squared. For the first shape, that is 1,500. For the second shape is 1080. All right, the second thing we calculate, that is we do the I calculation based on the table. So the standard I bar 1. That is 1/12. B is 100 and H is 15. $28, $125. And I value according to table for the second shape, that is 1/12. B is 12 and H is 90. $729. And the unit for these are millimeter to the power of 4. And then what about the distance of that center to here? That is D1. And the center of this one to here, that is D2. So D1 is equal to 7.5 take away from 29. $21.98. So D1 squared, that is 483. One, two. And D2, that is the distance of the second shape with respect to the neutral plane. So 15 plus 45, that is 60. So that is 60 minus 29.48. 30.52 squared 931. All right, now I need the product of di squared times AI. This is the penalty term. All right, now to find out the total moment of inertia, so we have to add all these values together, and that, according to the slide, the details are all right. So we find the total bending moment here, and that is all you need for the flexural formula. So from the bending moment diagram, we got the maximum bending moment in Newton millimeter. That is the maximum. This is the Y star. This is the points which are sitting here. This is Y star. And that is the total I, which we just calculated, all right? And then the number would be in megapascal. If you keep everything in Newton millimeter, the answer would be megapascal. Okay, so in today's tutorial, we because we ran the experiment last week, this week, Monday, we don't have the lecture. Lecture will be tomorrow. That's the tutorial for the stuff of the last week. So tomorrow I give you the last lecture for this subject. And then we have plenty of time to get exam preparation. We get prepared for the exam, run some sample problems in the class between now and end of week 12. So feel free to bring any extra question you want, any question you are interested, bring them to the exam preparation sessions into the tutorial. I'm happy to take and either solve them or give you a hint for solving those. Okay, let me finish the attendance, the roll, and then I'll be with you. Okay, so that is all we had for today's lecture. Any questions? Okay, no question. Thanks very much. I look forward to see you tomorrow. Thank you. Take care. Thank you, RC. Thank you, Porty. See you tomorrow. Bye.